Hello reviewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about how to use heat for cooling. So let's dive deep into it. So what exactly is the problem? Well, the planet is heating up. At this point in time, if any Tom, Dick and Harry is fighting about it, they're like, Earth is flat, let it go. So you have to understand, it is becoming brutal. And what does it mean? It means we are going from an era where AC was used for comfort to necessity, meaning this is India's few years ago, by the way. This places, basically satellite comes up with the data map. That data goes through what we call false colors. So you quantify the colors. Yeah, they messed up. They're like, okay, 50 degrees black. Okay, what do you show if it's above 50? They did not thought of it. So it's like, okay, fold the number data, it's white now. Like you must have seen digital camera also have that, like if some becomes over white, the number folds, it becomes black there. So same thing is happening here. It's supposed to be black, but it's like, yeah, you can't make black blacker than black. So it's like, okay, it's white. Yeah, that's brutal. And that's few years ago. And all the points aim towards the fact that India will be cooked in this year, as in like previous year was kind of nice. We had too much random rain that kept the temperature reasonable. Yeah, this time it's not looking like that. So it's hot, meaning things are getting out of hand and will burn. Now, here's the deal. If we do not handle this adequately, we're gonna create a worst feedback loop, meaning everybody will run AC. AC will make the outside hotter. ACs have to run longer because again, your house is not a perfect insulator. It's not like, okay, if outside is 70 degrees Celsius, inside of the house will remain 25. The leak heat input will overwhelm any air conditioner. So that creates a vicious feedback loop. And not to mention the most energy still is being created by fossil fuel. So that creates a very bad feedback loop. We must handle it without creating that sort of a feedback loop. Basically, we have to find a system which is less harmful. What we are doing is not sustainable. We need to have less harmful way. Again, will that solve the problem? No, but it will give us a fighting chance. So less harmful way of cooling ourselves without going to heat stroke, because you have to understand, once human body is at 20 degrees Celsius, your core to root temperature, basically core this part to this part, tips, is reasonable. It becomes 30 degrees. Of course, we can handle it. Again, I live in India. It's like, bro, this is normal for me. It's just that still your body is reaching closer to its operating limit. So if it reaches 40, yeah, you are in danger. So it's not like, okay, you're men can tough it out now. If the temperature reaches a certain point, your default temperature, as in your core temperature, reaches to dangerous limit. And God help you if you have a high humidity. For example, 40 degrees Celsius at 10% relative humidity, which is right now my current location, your body can easily cool out. Why? You will sweat will evaporate very quickly. Tada, your core temperature remains within reasonable limit. Now, you are same 40 degrees Celsius, but relative humidity is 80%. Some places are like Mumbai, basically places that are close to sea, places that are next to a river, yeah, your body is now a very severe risk of heat stroke. Why? You will sweat. Your body figures out, hey, core temperature overheating, engage sweat glands. Yeah, sweat will not boil off of you. Basically, it will not evaporate because water is like, bro, I cannot handle more water. So that's a very serious risk. Oh, this is from 2026. So that's why I said, like, this year we might cross this map. So fundamentally, we are reaching a point where we have to solve this adequately. Failure to do so will cook ourselves. And what if we use heat to move heat? There is no cooling. There is no such thing as cooling in this universe. All you do is leach heat away from it, dump it somewhere else. You can dump heat into something. You cannot dump cold into it. You only can extract it. So if we are doing extraction, what if we use heat for that extraction? So there comes heat pump. Now, heat pump is basically your air conditioning unit, this puppy. So all it does is takes heat from your inside, dumps it outside. Now be mindful, this is a new technology. And yes, I mean compressor, vapor compressor, those are new. Before that, we used to use fire for making ice. Then you're like, okay, why the heck we switched? We switched to vapor compression system as default nowadays because it has very good coefficient of performance. Meaning, if I give you 1 kilowatt of energy, 1 unit of energy, it can, in ideal scenarios, can leach off 3 units of energy from the area that you want to cool. So you will get massive cooling, meaning your AC would be like, I'm 1 kilowatt of electrical compressor power. It will only run for like, 15 minutes. It will leach off so much heat, your room will maintain the temperature. It's like, fine. So how do we measure it? That's what we call coefficient of performance, COP. And COP is complex vector because again it affects on too many things, but we'll talk more about that. Vapor compression has better COP rather than fire system, and it does have a limit. While COP is good, it does have a limit in terms of heat lift, meaning if this side and this side delta becomes too huge, basically you are trying to cool this to 10 degrees Celsius and this to 60 degrees Celsius, yeah, this compressor is like, bro, I can't do that. Like, it will work, but the COP will drop. So for example, if your indoor temperature have to be 25 degrees Celsius and your outdoor is, let's say even 40 degrees Celsius, you are looking at 4 COP. As in, for every unit of energy, you are leaching off 4. Great. But go to 50, now you are dropping to 3.1. And be mindful, this is industrial system. Most household AC will poop itself at 50 degrees Celsius. So, and I'm pretty sure this is an open, what you call, very high end system. This is like way too high COP in real world. So condensers reach a point where it's like, bro, I can't dump heat, and delta becomes a very big problematic thing. Meaning India, same AC, like I had this AC, it's the same AC if the outdoor was not hot enough. Basically, let's say it was only 35 degrees Celsius. I wanted 25 degrees Celsius indoor. It will be fine. It will be dandy. Enjoy, have fun. But the moment you change it, it's like, woof, the AC have to keep running on for longer. So there is a fundamental limit. And what are we seeking? We are seeking a liquid that boils at very low temperature. Why? It does not need to be very low temperature. While refrigerants we use in day-to-day life are like minus 18 degrees Celsius, minus 30 degrees Celsius, it's not necessary to go that low. Like, it helps at speed. The higher the T delta, the quicker the room heat boils this puppy, the quicker the flushing cycle happens. But it's not necessary. Especially if you are expecting to run the AC 24/7, that benefit of like having that very low evaporative temperature does not really matter. Actually, it backfires. So what happens is, this side is your room. So room heat goes into the fluid boils, which you call evaporator. Evaporator basically creates a basically low pressure, high temperature gas. That gas goes into your compressor. Compresses that puppy. Is like so once you compresses that, now you have high temperature, high pressure gas. Now that you put it into radiator, which we call a condenser. Condenser, it's hot. So you are running fan through it. Fan is dumping the heat. Now heat here was barely room temperature. Heat here is above, elevated, like 30 degree, 40 degrees Celsius. At that point in time, you run the fan, it dumps the heat, and voila, now it becomes liquid. But now be mindful, the liquid is not at pressure at this point, because again, it condensed, it's not at pressure. Pressure is here, is the liquid is not under pressure, but it's not cold. If you dunk your hand into your thermometer in the liquid is not that cold here. However, liquid goes into this valve, metering valve, and metering valve allows just a small amount, and voila, evaporation, and voila, this part becomes cool. So this is the compression system. And again, delta is the key. If you want to have very energy efficient system, just make sure the condenser temperature is maintained, or as close to as possible as your final point. And again, be mindful, if you are expecting to run your AC for very long duration, many times you will find that. Like household ACs will use a refrigerant that goes very low temperature, because again, it makes it very rapid. Industrial system, because they have to maintain the system like 24/7, they're like, yeah, that backfires on you. At that point in time, hey, you do not want the low to go that low. So it's like minus 10 degree, we good, we got this. So that sort of refrigerant makes far more sense. Even though flux rate becomes slower, because you are running 24/7. Once it cools down, and it's not turning off. So you're good, you got this. So low temperature evaporation is the key. Meaning, if you can evaporate below room temperature, you're good. For example, if you want to cool down the room to 20 degrees Celsius, you only need to liquid to evaporate at 15 degrees Celsius. You're good at that point in time. And you can do that with water. Water has a vector which we call pressure, meaning if you want water to boil at a lower and lower temperature, all you have to do is pull it closer to vacuum. For example, you can boil it at 22 degrees Celsius as almost 0.1 psi, meaning the closer you go to vacuum, the more quickly it boils. So even little bit of heat, room heat, boils it away. So that's the heat pump logic. Now we come to absorption chiller. Be mindful, this is the worst word, because if you change the B to D, it's a different technology. So absorption chiller is an industrial puppy. Basically, imagine you are running a coal power plant, or running a diesel power plant, or a jet engine power plant. You have bonkers amount of heat, like 100, 150 degrees Celsius. So you take bonkers amount of heat and you load that puppy, like you boil things from it. You take that, you have cooling water, meaning you do have a place where you're dumping all that heat, because again, heat pump only takes heat to and moves it again. So you do need a sink for it, as in like atmosphere, where you're dumping all the heat. And you will get the chilled water. That's your cold refrigerant, as in the chilled water would go run into your fan coil unit and cool down your room or your equipment if you're trying to do that. This puppy can go low temperature, as in like -5 has been achieved, -30 has been achieved. It can go cold, like cold. So, but it does require hot temperature. For example, in this design, the hot is 90 degrees Celsius, output is 80. Basically, you pump 90 degrees Celsius hot water, you get 80 degrees Celsius hot water out of it. Your cooling water is 28 degrees Celsius, it comes up to 35 degrees Celsius. And your chilled water is 12 degrees Celsius and it gets cooled down to 60 degrees Celsius. That's exactly the temperature that is used in district cooling temperature, almost the same range. So if you have to cool a district and you have a jet power plant running 24/7, using this makes sense. It's like you are converting fuel into electricity. Only 30-35% would be converted into electricity. Most would be waste heat. Why would you want to use the electricity that is only 35% to run AC again? It's not ideal. You have so much waste heat, even if coefficient of performance is low, because you have 70% compared to your electrical system. Why not use that? Even at lower COP, it makes more sense, more direct. So that's what we call combined heat and power, or cooling and power. At that point in time, you can, instead of having 30-35% efficiency, useful efficiency goes to 60%. That's why I said lower, what we call lower feedback loop. Or if you're running an industry, you have certain places, like a steel furnace and all that, like you collect that heat and get the cooling. So people, all the electronic units that needs cooling, all other processes that require cooling, you're cooling it from the waste heat. Coefficient of performance is not great. That's why we abandoned it, 0.7 to 0.8. But again, there are certain new ones that can touch 1.4. Now 1.4 from an industrial compressor point of view is like, what is that? But from a household, actually reasonable. Household AC does not meet 1.4 at like high noon temperature, so to say. So not too bad. Like, it was unreasonable back in the day, but today's overheating temperature, this is like decent, so to say. And how do you achieve this? Well, you take your chilled water that is running on a loop. In that loop, you spray water to it, distilled water. You spray that water and that water goes onto the pipe and leaches heat from it. But this area is partial vacuum, so it boils. Basically, the liquid to phase change happens and it becomes liquid to gas. Now you have vapor pressure. But again, once you have vapor pressure, the vacuum will not be maintained. It will, like, vapor pressure is there. So you need something that will drink that vapor. Ta-da! Absorber. Absorber is what we classify as lithium bromide. Lithium bromide is a naughty sauce. That sauce will drink water. Like, you put it in a bucket of water, it will drink more water. Like, your bucket will fill up more. That's how thirsty this puppy is. So this absorber will absorb all the vapor. So your partial pressure is maintained there, meaning you can literally maintain vacuum there as long as absorber can maintain the flow rate, so to say. So now your absorber is saturated. It already got married to water. So it's like it needs divorce now. So you send it to what we call generator. Generator is your main workforce. You heat that puppy up. Code case, like, you heat that puppy up. After you heat it up, lithium bromide just gets, bruh, I can't handle this. It dumps all the water. Now here's the deal. That vapor pressure is now high. So you need to drop it down again. So at that point in time, you have the cooling water. Cooling water absorbs the vapor to liquid phase change, takes all the heat, that is the waste heat, and dumps it into your condenser loop. And voila, condenser takes it everywhere away. And then you have absorber running it again. So here you are saturating it, you are desaturating it, saturating, and you get fresh water from condenser side, which continues the evaporator cycle. So it's literally just what you call your compressor system. Like, you have evaporator, you have condenser. Only the compressor has been replaced with absorber and desorber. So absorber eats up the water and desorber dumps the water. So cycle repeats. And again, it does require plumbing. Like, unless you are comfortable with three-dimensional plumbing, don't try to look into these sort of mechanisms. It will cook your brain 5 ways to Sunday. And I dare you to look into double effect or triple effect systems. Those are very efficient, but goddamn, the flow chart is like, are you serious? Now be mindful, I'm talking about water and lithium bromide because that's the most likely. If you randomly pick up a phone, Amazon, yo my man, I need this, most likely they're gonna give you a lithium bromide and water solution. There are water and ammonia solutions also. There are some other specialty, but most of them are very rare. 99% of the time you're gonna buy lithium bromide system, and cycle repeats, vacuum is maintained, and you end up with three system. You have cooling tower system, you have hot source, and then you have chilled water. Be mindful, it does have a certain what you call complexity, because you are talking about a salt that is in water. Your metal has to be decent. You cannot use Chinesium cheap metal. It has to be quality metal, otherwise this thing will go kaput. Thankfully, India does have this technology, like world leading kind of technology, as in top few sellers, one of them are Indian. I have linked the video down below. Like, we've been doing this surprisingly good, like we're good at it. So you evaporation, absorption, generation, condensation, the cycle repeats. It's basically cell and tube heat exchanger, boatload of them, and a lot of pumps. So that's absorption chiller. This puppy works, but does require hot, as in like hot 18, 90 degrees Celsius. Be mindful, that's a conservative side because the cooling tower is cold. If your cooling tower is not cold, as in like 28 degrees Celsius, which again would be winter in India, this driving temperature can go 150 or 200. And once Japan went kaboom with Fukushima, they had a problem. It's like, how the heck you cool the buildings? Because again, building cooling is important. It will become unlivable instantaneously without that. How can you do it? Well, they're like, hey, we had gas pipeline. Directly feed gas into this, because here's what else could you do? You take the gas, run it into a generator, and then voila, waste it. Or you can take the gas, feed it into this, and voila, directly far more effective. So people use that. And some places which again, you do not want to do generator. These things can run 24/7 for a very long time. While your fire boiler, that can also run 24/7. Generators are not designed to run 24/7 for very long duration. So absorption chiller is a very clever utilization system. So if you have a source, heat source, that is just regular, like coal power plant runs 24/7, this is your guy. Like for example, in New York, they have coal power plants or power plants, so to say, and the waste heat is dumped into city heat system. What if you have district cooling, and instead of getting like steam, you are getting this absorption chiller cooled water, chilled water. 12 degrees Celsius is input temperature, output temperature is 6 degrees Celsius. You get cooling, and this big turbocharges your energy efficiency, because otherwise people will use the electricity to run the AC. What's the point? So absorption chiller is a really good large-scale solution for district cooling sort of system, industrial players, heavy puppies. Let's just put it that way. It's great. It does work. And again, more demand of this happened just after that Fukushima thing. And a lot of research has been going on that triple stage designs. But again, hot does require to be hot. If you can achieve that, this puppy, and again, my best use case would be dump it with what we call coal power plant as a battery backup. You still have waste heat, use it. People complain now that electrical conversion efficiency is very bad compared to battery. Why not use it something useful? And again, we're gonna need district cooling. It is one of the least feedback loop amplifiers, so to say. Compared to household refrigeration, that is exponentially better. So this is a very useful technology for big loads. Now we come to something for small puppies. Adsorption, D. Adsorption chiller. This is what we classify as solid state. Now let that be clear, we call it solid state because the desiccant is solid. You are not talking about lithium bromide solution. We are talking about water and solid desiccant. That could be silica gel, it could be zeolite, those sort of things. So you get chilled water, but again, this does not go cold, like cold, as in like it will most likely will not freeze water. So you're talking about like 5 to 15 degrees Celsius water. Now, is that sufficient? Here's the deal. Places where I'm thinking about utilizing that, we're gonna be cooked. So 15 degrees Celsius is good. Any temperature that is below dew point temperature will remove humidity from the air. We good, we do not need more than that. Like if you have nothing else, if you just have this system, we good. And again, 5 to 15 degrees, we have to shut it off. And again, we do run this sort of system, so we know that fan coil unit does not require like minus 10 degrees Celsius water. We find with 15 degrees Celsius, like it will still dehumidify. Again, it will be slower, but it will work. Coefficient of performance is horrendous in this, 0.4 to 0.6. But again, that's why these sort of system only should work from a free heat source, either solar or waste heat. So coefficient of performance is bad, like 0.4 to 0.6. Some people are claiming they have advanced system that can touch 1.4. I have looked through multiple PDFs, none of them specify it. They're like, high COP. I'm like, how high? What is the condenser? Basically cooling water temperature. They talk about the hot source temperature. That has gone down. Like when this sort of technology started, we were like, we will be lucky if we can get anything below 90. Now you can buy things, company will certify it for 50 degrees Celsius. But the cooling water has to be cold, like 30 degrees Celsius. In India, I need something that works at like, 70 degrees Celsius, while the cold water is only 45. That delta has shrunk, or basically what we call low grade heat. This can work in low grade heat. COP won't be great. The cooling will not be GG, but it will still cool and it will not consume water. So that is there. The H2O is a refrigerant, sealed system, it does not leak it. H2O is absorbed. So what you have is chilled water. Water is sprayed here, pipe heat of the chilled water dumps into the water vapor, as in like the water droplets evaporate, goes into this chamber. Now in this scenario, this chamber is active. The chamber absorbs it, so you do have to cool it because absorption will dump some heat. So you want to cool it, it will consume, and the more it will consume, the more this area will become partially vacuumed, the more cooling action will happen. This will get saturated, then you close this tap, then you open this tap. So this tap is basically, now you have force feeding the hot water. The hot water in this design is like 90 degrees Celsius hot water. Once you have that hot water, now this will dump all that adsorbed water, meaning the water that was attached to the surface, it will just heat it up, go into the condensing unit. The cooling water will condense the water and the cycle loops. But be mindful, this is not a closed cycle. This is not a flow continuous like a refrigerant cycle. It has to be done in blocks. So that's why they will always say flapper valves. It does require valves, and not to mention that itself is not that difficult. It requires the water plumbing to change, meaning you need four-way valve, meaning cool this side, heat this side, cool this side, heat this side. You have to do this like tan, 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 while maintaining the valve system. So it is bit more messy, but again, we humans know how to make this. Like, have you seen internal combustion engine? This is minor inconvenience. So in this design, like this is 90 degrees Celsius, water goes in, 83 degrees Celsius comes out. Cooling tower water is 30 degrees Celsius, 38 degree goes out. The chilled water is 12 degrees Celsius to 7 degrees Celsius, more than decent enough. And again, that's what I'm thinking, like what if I fine tune the system so this water goes up, as in like 15 to 20 degrees Celsius. I don't need much more than that, again, for household or even office, because again, alternative is running AC at that point in time. And if it's running on the solar concentrator, not only your building is not getting solar heat, you are using the heat to pump the heat. So coefficient of performance is bad, but again, solar heat is free. And what about the pumps and all that? Those are negligible. Like systems that are like multi-kilowatt, like 10 kilowatt unit. This is like a 10 kilowatt unit setup. That puppy only consumes like 600 watts of power. That's just auxiliary pumps. So creating low pressure gives you that action, the evaporation at low temperature action. That is your cooling. That is giving you the cooling system. And your condenser has that waste heat. You do have to have a massive heat, tower, where you're dumping all that heat. But again, a manageable system. It does require valves and plumbing. It's a bit messy. I have not seen anyone who has figured out a design that is like static, so to say. So it is messy. And again, for example, let's just say temperature is not that bad, okay? It's not that bad. You can live through it. But it's moist, like next to sea. It's not bad, but again, because of the humidity, it's brutal. At that point, you run the system in open loop. You can just have a desiccant wheel that can run in open loop, and voila, you are just dehumidifying the air. Much better. So, and again, that will be even more efficient. Here you are trying to get the cooling, so it has to remove heat, then condense the water. That will only leach the water away. So it's far more like quick, rapid in terms of dehumidification. So this is what we do. Waste heat will be bigger because again, coefficient of performance is lower, but again, temperature is lower, so whole flux would be high, but the temperature would be lower. So what can we expect in the future? Well, here's the deal. India is getting too close to cough temperature, meaning we're going to be dead. Meaning if the temperature keeps rising at this point in time, by 2035 or even 40s, it's looking bad. We have to hope rain every day, otherwise we will be cooked off. Because again, this has an upper limit. How much hot air can go inside it and you still survive that, that's very limiting. So, and again, you cannot have a scenario where Indians have to become like a vampire, so it's like, do not go out in the sun, only at night. So we have to do something. Basically, we have to do the cooling without making us worse. And again, if you're burning fossil fuel, might as well use the waste heat. So that will give you more for least amount of CO2. great. And again, economically also great. So it's just that initial capital cost that you have to push through it. And then again, it makes sense. District cooling has to be done. There is no alternative to that. And again, India is trying to get into district cooling. There is one project that is next to Ahmedabad in Gujarat that is trying to do that. But again, we are a bit behind schedule on that. We have to get it like ASAP. So that is it. Industrial customers, they have to go to absorption chiller now. Now, I was always curious, how can India have solar panels in the future? Because again, solar panels cannot like hot temperature. Like for example, I have to say, Wari is the only one where I can find it easily. If you buy a solar panel in India, we have a standards body, ISI, Indian Standards Institution, I think. Not institution, something like that. So this ISI body validates everything, electrical appliances and all that. Now, they have validated on European units, as in 25 degrees Celsius. India is not 25 degrees Celsius. That's winter for us. So what happens if your solar panel goes hotter than that? Yeah, your voltage starts to drop. The current output goes down, as in like the total output of energy goes down. So this plate at 25 degrees Celsius, for example, would be rated to 50 volts. And if it's in winter, like really winter, like in Himalayas and all that, that will be 10 degrees Celsius. At that point in time, you'll get 55 volt. But here's what will most likely you'll get? Yeah, you will get 70 degrees Celsius, the voltage will drop to 45. So that's the main issue. Not even 45, oh yeah, 43. So something that's supposed to give you 50 will drop to 43. Even if the current is the same, you know, the total output went down. So that's a big issue. And solar farms that we are placing, it has an upper limit, meaning even this solar cells have a limit where it's not like, okay, at 80 or 90 degrees Celsius, it will just like, you know, produce a bit less. No, it will drop drastically, and not to mention lifespan will also be shortened. So is there a solution to this? Thankfully, yes. I have no idea how the heck Europeans are the first to solve this. They have PVT panels, as in the solar panel is there, on the back there is a solar heaters on there. I'm like, how the heck Europeans figured it out? Now I understand that they have cold, so they like directly use the heat, but like they also have to worry about it being freezing. So water like and all that. So somehow they figured it out, we haven't. And it's much easier for us, like water rarely freezes in India. So we have to have that. That will leach all the heat away. And for example, if you have a solar rooftop that is 10 kilowatt, you'll get 20 kilowatt of thermal energy. That's more than enough. That's why I said the COP does not matter. Even if the COP is only, let's just say 0.25, you good. That's still like 10 kilowatt surface area. That gives you 20 kilowatt of it. 25% of that is cooling. That's like a lot. Like almost 5 kilowatts continuous. And again, it's not making the situation worse. That's the biggest part. It's not making the situation worse, it's making your life better and making your solar panel last longer. So it's double, triple whammy. So PVT panels have to be the future replacement of PV panels. That's how we can make sure the panels last very long. This is European thermal camera footage, and you can see this puppy is already at 60 degrees Celsius. So, and that's the easiest way to figure out which panel is broken. Look it through infrared camera. If one of the cell is overheating, yeah, that panel is about to go kaput. So that's the whole system. And absorption chiller, like this sort of system, can be tuned to work with low T deltas. Physics allows it. We just have to fine tune it. Basically, cooling water is the main limitation. And this sort of PVT, while it does give you hot water, it does have a lot of flux. It does not have T delta. Like for example, if you had like vacuum solar collectors, those puppy will get hot, like hot. This will not get hot. It has the heat, it's just not hot. You just have bonkers amount of flux, like lot of amps, very low amount of voltage. That's why I said like COP will go down. But again, you can run a cooling tower, and again, we can do double dipping on that. We can have like about open loop cooling tower, as in like a cooler evaporated. So that way we can get more out of bunks. For example, if temperature is not cooperating. It has to be done. This technology we are talking about, it has to be done. And I mean everywhere. India, we need to do it yesterday. All of you guys, no matter which country you are in, you're gonna need to do it soon. I would say 2050, if I'm being optimistic, assuming that methane runaway does not happen. If that happens, bye-bye. So this is the critical reality. We have to do that. Thankfully, technology exists. I have been told with a guy who works in this sort of system, it's like, there is a company that is trying to bring PVT panels in India, and I'm like, please bring it. We need it more than anyone else. How the heck we are the last one who's getting it? So let's see how it unfolds. Or again, by the way, you can even do other things. For example, you can cascade it with your normal condenser systems, as in like normal AC system. So AC will dump all the heat into the air as much as it can. After that, this absorption chiller is like, let me cool down your more. So what does it mean? That means COP goes up. So your COP, instead of barely achieving 1, it's like, bro, I'm like 2, 2.5, even at peak summer. That's like, shut up, take money. So there is a lot of scope now. I was like worried, like what can we do with hot water in India? We can run clothes washer. They like hot water. We are new to getting dishwashers. Again, they also need hot water. That's great. Clothes drying. Again, we generally put it in the sun. But if you do not want UV bleaching of your clothes, doing indoor will require hot water. We got this. As in like hot water running on a radiator in a cabinet. It's doable, nothing fancy. But running AC on it, everybody will do it. Everybody is like, let me do it. Like again, at that point in time, the solar panels and electricity, that's just like, if it has enough electricity just to run a heat pump, just to amplify the temperature delta, basically like a DC to DC converter, it's gonna be fine. So we have option. Like we have reached a point where the COP advantage of normal ACs are already evaporating away. Might as well switch back to the older technology, 2 century older. So this was my presentation on basically how can you use the heat to do cooling. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.